Hello guys, now let us prove theorem 3 on homeomorphism. A bijective function, a bijective function, okay, f from where to where? From x to y is a homeomorphism if and only if f of a bar is equal to f of a whole bar for all subsets a of x. Okay. So now, what is basically given? Basically given the function is bijective. Basically given, so let me write that. So basically given f from x to y is a bijective function. They have given f is bijective. And there is if and only if in the theorem. So we have necessary and sufficiency. For necessary, what is given? For necessary, given that the function f is a homeomorphism, correct? The homeomorphism. Done. Okay, what we have to prove? To prove that for all subsets A of x, we have to prove that f of a bar is equal to f of a whole bar, right? Okay. Now, we have to prove these two are equal, right? Okay, yes. Since, have you seen this somewhere? Something like this? Do you remember? Okay, let us see. Now, since what they have given, f is a homeomorphism, no? That means what? F is bijective, f is continuous, and f inverse is continuous, or f inverse is continuous. In other words, we can also tell f is open mapping, right? Okay. So, since f is continuous, we know that for all subsets A of x, we know that f of a bar, remember this relation, is contained in f of a whole bar. Whenever f is continuous, we have this, right? We'll call this as equation 1. What we have to prove? We have to prove both are equal, right? So I got one side, right? What else we have to prove now? So next, to show that I want the other way. What is the other way? F of a whole bar is contained in f of a bar. This is what we have to prove, and we can call this as equation 2, and 1 and 2 will imply that they are equal, right? Okay. Now, very simple. Now, let us consider what we have a and a bar. What is the relationship between a and a bar? So we know that a is contained in a bar, correct? A is contained in a bar. Whenever A is contained in A bar, what about the images? F of A will also be contained in F of A bar. Agree? Yes. And what is A bar? And definitely A bar is dash. What is the dash? Closed. Remember, once you put bar, it is closed. So A bar is closed. And F inverse is continuous because F is a homeomorphism, right? So F inverse is continuous, that is given. Whenever F inverse is continuous, right, we know that inverse of a closed set is closed, right? So we know that inverse of, okay, that is F inverse, F inverse means what here? You can put a bracket for this. So inverse means F inverse whole inverse of a closed set. Closed set is closed. Inverse of a closed set is closed, right? So F inverse whole inverse is nothing but F only, right? And what is A bar is closed, no? So I'll take that F of A bar is closed. Understood? Because A bar is closed, we have F inverse is the continuous function, and we know that inverse of a closed set is closed. And inverse means here we are taking this F inverse whole inverse. Okay, inverse of this F inverse. And F inverse whole inverse is nothing but F only. So F of A bar is closed. Now F of A bar is, this is closed, this is closed, right? And contains F of A. So you have one closed set containing F of A. And what is the smallest closed set containing F of A? So next is the smallest closed set. And the smallest closed set, the smallest closed set. So what is the smallest closed set? And F of A whole bar is the smallest closed set what? Containing F of A, right? Containing F of A. Now combine these two. So you have one closed set containing F of A, and we have the smallest closed set containing F of A. So we'll imply that which is the smallest one? Smallest one is this, is contained in this closed set, that is this F of A. This is what we had to prove, no? And we got it. We'll call this as 2 from 1 and 2. From 1 and 2, we got their C. F of A bar is equal to F of A whole. And this happened for all subsets A of X, hence necessary. So necessary is done. Hence necessary. Okay, now sufficiency. We have to prove sufficiency. What is sufficiency? Very simple. Sufficiency, what is given? Given what they have given? For all subsets A of X, they have given F of A bar is equal to F of A whole bar. That is what they have given. And what we have to prove? We have to prove that F is a homeomorphism. PPT to prove that okay, F from X to Y is a homeomorphism. What is homeomorphism? We have to prove F is bijective, F is continuous, and inverse is continuous, right? So now first one, is it bijective? F from X to Y is dash. Is it bijective? Is it bijective? Why it is bijective? Because it is given. Remember in the beginning, the statement of the theorem says that a bijective function, correct? So F is bijective, that is they have given. F is bijective. Second one, is it continuous? They have given what? They have given for all subsets A of X, they have given F of A bar, okay, is equal to F of A whole bar, right? Now can I take the one side? One side is enough for what? Is contained in F of A whole bar, correct? No. So what does that imply? So this implies the function F is dash. Function F is continuous. This implies the function F is continuous. We know that whenever the function is continuous, F of A bar is contained in F of A whole bar for all subsets A of X. Agree? Yes. So we proved it is bijective. It was given. We didn't prove that it was given. And second one, we proved it is continuous. Now what we have to do? Third one, to prove that or to show that F inverse from where to where? Y to X is continuous. Right? And what is the alternative statement of inverse is continuous? Or what? Or we have to prove that f inverse is continuous, or f from x to y is an open mapping. We know that these two are equivalent. So we can prove this is an open mapping. Okay, what is an open mapping? Takes open sets to open sets. Okay, so where we have to take the open set now? So let U be an open set in X. And we have to prove f of U is open in Y. Then our f is an open mapping. Right? Okay. Now, U is open set in X. So what is X minus U? Complement is what? Can you guess? Closed in X. So it is closed set, no? What is the next step now? What is its bar? Whenever you have a closed set, what is its bar? That implies X minus U bar is equal to itself, because it is closed. It's closed, so bar is itself. Right? Now, this X minus U is subset of X. Correct? What they have given? For any subset of X, what is given? So, for all subsets, okay, A of X, they have given what? They have given f of A bar is contained in f of A whole bar. I mean, is equal to. Correct? No? They have given it is equal to. They have given it is equal to. So, this equal to. They have given it is equal. Right? Now, what do we do? Replace. In this, we are going to replace A by, I want a subset of X. What is the subset of X? It is above there, right? So what is the subset of X? X minus U. So we are going to replace A by X minus U. Okay. So in this, just replace X minus U. A place only X minus U half become. Okay, that implies now, now wherever A is there, we are replacing. So F as it is. In the place of A, I am putting X minus U. Bar remains as it is equal to f of A plus only X minus U and whole bar as it is. Right? And what is X minus U bar? X minus U bar is nothing but X minus U. So bar plus only X minus U. So this implies f of X minus U is equal to f of X minus U whole bar. You have A equal to A bar. That means what is the next step now? What is A equal to now? Whenever A is equal to A bar. That implies, this implies this f of X minus U is closed. Closed image, no? So it will be in Y. Closed in Y. So now what is the f of A minus B? F of A minus f of B. F of X minus f of U is closed in set Y. And what is f of X? Any guesses? What is f of X? F of X is nothing but Y. F of X is nothing but Y. Okay. Because f is dash. Can anyone guess? Because f is bijective. In that bijective, that onto part. Right? Minus f of U as it is closed in Y also as it is. That implies f of U is dash. Is open complement, no? In, remember what was our U? U was any open set in X. And we got f of U is open in Y. So f is taking open sets to open sets. So therefore, f is an open mapping. Therefore, this implies F is an open. F is an open mapping, or F inverse is continuous, right? So by 1, 2, 3, 1, F is bijective, number 2, F is continuous, and number 3, that is nothing but F is an open mapping, right? Therefore, what is F? F is homeomorphism. Homeomorphism. That F is homeomorphism, no? Hence, we have proved the sufficiency part of the theorem. Okay, guys? So, theorem 3 is completed.